So good morning to all. I think today is the last session of this winter school. So ma'am will now give the presentation on addressing data imbalance issues. Okay. So after that we have question answering session, and Pushpa ma'am and Sulagna ma'am will give some assignment. Fine. So you have to submit the assignment. Ma'am will tell you the date, how many days she is going to give you. Then whenever after submitting the assignment, we'll ask you to give some this presentation, and during the presentation only we'll take some small questions or interview, you can say. So after which we'll select some students, 10 to 12 students maximum we'll select. So this particular session is very important, because after that only question answering session will be there, and assignment also will be given by the Sulagna ma'am and Pushpa ma'am, and both will join after this session. So if you have any queries, questions, suggestion, or verbal feedback also, you can give. Okay, so no problem. So by 12:20 we'll finish everything. So 10 to 11:30 sessions, or before that also ma'am will complete. After that, followed by your this one, your question answering session. Okay, so is it clear to you? So Sulagna ma'am, my session is yours. You can start.
Thank you so much, sir. Let's start today's session. Okay, good morning, all of. Just a minute, why it's echoing? Okay. Okay, let's start. So today we are going to discuss about the topic was actually addressing the imbalance data, but last time some students asked about the number of parameter analysis or how to reduce the computational complexity. Like currently actually many models are there, so people are not only now focusing to do the computer vision task like classification or segmentation or detection. Now researcher also they are now deviating from the traditional research. Now some like good papers are actually published how to reduce the computational complexity. Let's say one model's parameters is like 103 billion, and all param like for all application, all the layers or all the number of filters it is has in the traditional network, not really like applicable to all application. Why not we will reduce some parameter and we will maintain that accuracy or with little bit less accuracy, because if some model give us already 95% accuracy but the parameter size or the compute time complexity is really high, why not just reduce some parameters value computational complexity and maybe the accuracy 1-2% is adjustable. So considering that trade-off, now people are publishing also many paper. But of course, that due to lack of time, their work we couldn't show you here. But I will show you like how you can calculate the parameters or the other performance metrics for the model evaluation in one model. So let's discuss about that. So first part is the CNN model evaluation. This is just for some minutes I will spend some time here. But next we'll go for to handle the data imbalance problem or the class imbalance problem. So generally, for the CNN inference, when we have convolutional neural network, we not only go for the performance metrics like accuracy, specificity, sensitivity, or precision, recall, or F1 score. Apart from that, also in the current publications, and people are also adding some of the evaluation parameters. Well, what are those? Mainly these 5 parameters, the number of parameters, flops and flops. Please pay an attention. This flop is small s and this flop is capital S. That is the difference actually. Then max and inference time. So what are those that we will discuss? So I will show you how to calculate the number of parameters, and but before that we will discuss about what is this flops and some theory related to that. Actually, this flop, a small s, it stands for it will measure the inference time for a model, like total number of computation. It generally flop stands for floating point operation. Means this small s is nothing but in your model, because we have already shown we have different filter, we have feature map, we have stride, and there is a convolution operation, there is some multiplication operation, there is some addition operation, there is some subtraction operation. So in those operation, when we will do, so that, like, how many operations are already there, because when the machine is going to do some operations, there is definitely be some computation needed to perform those computations, and also it needs some time, so there is some computational complexity as well as some time complexity are added to that. So this one is stands for small s. Small s, generally we go for like the all the mathematical operation that we will do, and it gives us the computational complexity of our model. Then the capital S actually floating point operation per second. That's why there is a capital S. So this one is something related to the hardware part. Like when we are going to buy a GPU, generally we ask the vendor what is the flops capacity of that one. Generally they say, okay, we have the CPU or GPU that performs 1 gigaflux or something. It is something like what's the hardware capacity, because based on your hardware capacity we can calculate the small s. So that's the relationship of between that. Small s is how much, like, the computational complexity of your model. Capital S is like what, how much like the complexity your CPU or GPU can handle per second. Then we have MCS. MCS stands for multiply accumulate computation. It can also, it will helpful for addition and multiplication, no subtraction or no other operation. It will mostly focus on addition and multiplication, because convolutional neural network is mostly addition and multiplication operation. It will take on state of the art convolutional neural network. So if I go for the relationship, generally capital small s and MACS relation is 1 MAC is equal to 2 flops. And inference time, generally we calculate small s capital divided by capital S, because what is the computation of your model complexity? Sorry, what is the computational complexity of your model, and how much for like the GPU, your CPU, you can handle that computational complexity. So that division will give us inference time. So considering this relation, now we will calculate the number of parameter, because that one is also very, very important. So how to calculate the first part, the number of parameters. So here I am for calculation, I have considered the BGG16 model that we have already discussed many times throughout this these classes. So let's see how these parameters are calculated. So this is actually the total BGG16 network. It is having like the 16 layers. This one is the first convolution, then second convolutional layer, then third, then fourth, then we have in between the max pooling layer. And this is the input channels. Input channels means when the image we are just inputted, the number of channel is 3, R, G, and B. Sorry. And then these are actually the number of filters we apply to the for the convolution operation. Then after application of those filters, then we have with some feature maps are generated. So how many feature maps are generated? These are the output channels. Then what is the input size to the next convolution layer, because it is like sequential one after another. Then what is the kernel size? Like each filter contains certain kernels. So what is that kernel size? That part in the classification class I have already discussed. Then what is the striding and what is the padding value? So based on that, what could be our output? So these are actually the total BGG16. This is the if this is the input, if this is the number of output channels we are giving, if this is our input size, if this is the kernel size, if this is the stride, this is the padding, this is our output size. If this is our network, then how we calculate the parameters actually? First, go to this one, the input layer, the red color part, because it's just the input. So we are nothing going to learn here. So the number of parameters is 0 here. Now we come to the next convolution layers. Here the formula, here the parameter calculation. What's the formula is? WC is equal to number of weights of the convolutional layer. Here the weights nothing but the input channel is, sorry, this one the kernel size, which is 3 cross 3. Then BC is equal to number of bias. So the bias is here is equal to 3. Why 3? Because each weight is considered, each always include with 1111 bias. So that's why as our number of weights is equal to 3, the input channel. So that's why our bias is equal to 3. Then PC is equal to the number of parameters in the convolutional layer. Here actually it is not the parameters, it's the number of input channel, sorry, number of output channel, which is the 64 value. Then K is the size of the kernel. Size of the kernel is 3 cross 3. Then N is the number of channels to the output, which is the 64. Then the number of channels in the input layer, then which is equal to 3. So putting in this value, when we will calculate, first one is first we calculate the WC. WC is equal to K square cross C cross N. So what is our K square? K square is nothing but the size of the kernel. So what is the size of the kernel? The kernel size is 3 cross 3. So that's why we put here 3 cross 3. Then what is capital C? Capital C is the number of channels in the input layer. So what is the number of channels in the input layer? The number of input channel is 3. So we put here 3. Then what? Then the next one is N. What is N? Capital N is nothing but number of output channels. So how many output channels we have? We have output channels is the 64. Then you will put these values. Then we got 1728. Then BC is nothing but our number of biases. I have already said that each number of bias is equal to the number of input channels, because each filter is associated with 1111 bias. So BC is equal to N. Here our number of output channel, this one is 64. So our bias is also 64. Then the number of parameter is equal to WC plus BC is equal to 1792. So from the past convolutional layer, the number of value, the number of parameter we have calculated is 1792. Then move to the next one. Now in the next one, similarly, when we will calculate the number of, we put this value like the what is the your kernel size, what is your output channel, what is your input channel, what is your bias. Then we got in the second convolutional layer, the value is, the parameter is 36928. So this many number of parameters are there. Then the next max pooling layer, actually in the max pooling, we are not going to do any kind of operation, because there is a window only there, and we are calculating which one is the max feature map value. Or so for max pooling, there is no mathematical like operation. So the number of parameters is 0. Then we move to the next convolutional layer, then putting all those value, when we calculate, then the value is 73856. Then further we'll move to the next convolution layer. Then if we'll put all those value, then we got 147584. Like this, when we will move all the convolutional layer to calculate the individual parameters in all layers, then you will see the final parameters at BJJ 16. Here you can see this big value, 138 million approximately. So when this model will run for any classification task or detection task or for your segmentation task, then only from the feature extractor part, you only get like 138 million parameter. So it's really huge. So now the researchers, they have developed some algorithms, how efficiently we can, because the number of layers involved will increase the parameter, and not only the number of layers, as well as the number of input channel. Input channel means how many filters we are applying. Number of output channel means how many feature maps we are generating, and the size and the stride. So how can we reduce some value, or how can we reduce some parameter, how can we reduce certain parameters so that our overall parameters will be reduced? Actually, most of the researchers till now is working on 3 types of work. First one is how to reduce the convolutional layer. Suppose here we are using 13 convolutional layers. How that 13 convolutional layer we can reduce to 8 and 9 by still maintaining the like the accuracy. And also another research is like number of filters. Why will apply 256 number of filters? Why apply 512 number of filters? Why not little reduce to that? And the next thing is the output channels, because it find that some when we apply the filters to the model, sorry, to the convolutional the feature maps, then we will find out all output feature maps are not containing the valuable information which has some importance towards classification, segmentation, or detection. Even if in the experiment we have found some feature maps are just empty. So how to reduce those uninfluential feature maps or which have no contribution towards the good accuracy. Actually, in my PhD, I have worked in this part, how to reduce the output channels and the number of output channels and keep only the important feature maps. So maybe some other day we'll discuss my idea to that on that. But we have some already some like the formula, and we have already know the input channel, output channel, and these things we have already known from a network. We are just putting those values and we get some like the output, so that we can know for this model we have this many number of parameters. Then we'll move to the flops, how the small is calculated. It have also some formula. For convolutional layer, they have like formula KH into KW into C in multiplied with C out plus C out into H cross W. What is C in? C in is the number of input channels, which is nothing but your number of filters. And C out is the number of output channels, which is nothing but your number of feature maps generated. Then H and W is your width and height of the feature map. Then KW, KH is equal to width and height of the kernel. So by putting this value, when we calculate like the value for only for convolutional layer, then when we have the fully connected layer or dense layer comes after the classifier, then the formula is n in into n out plus n out. N in is the number of input neurons, and n out is equal to number of output neurons, because in the last dense layer we have the neurons and which are responsible for give the classification. So what is the number of neurons present here and how many number of inputs are giving to the neuron? So considering those value, when we calculate the number of flops here, like I'll discuss like in a layer by wide, so that you will have a clear idea how generally the flops is calculated. For the first convolutional layer, our input size is 224 cross 224 cross 3, because this is the default size, which is 16 Hz. Then for the fast convolutional layer, the filter size or the kernel size we have mentioned 3 cross 3, and the number of filters is 64, padding is equal to 1, stride is equal to 1. Then the output feature map is 224 cross 224 cross 64. Actually, there is a formula also how you calculate the output feature map size. After putting this one, let's say we get 224 cross 224 cross 64. Now considering these values, when we calculate the number of flops in this layer, if we put this value, our KH and KW are width and height of the kernel, which we have 3 cross 3. Filter size means, you can see some people also say it's the kernel size, because filter is nothing but consisting of some kernels. So this one is like 3 cross 3. Then C in is the number of input channel. Our number of input channel for the first layer is RGB. So this is 3. So this is 3. Then we have also 64, C out. What is the number of output channel? The number of output channel is 64. Then we have our H cross W, like width and height of the image, which is 224 cross 224. So putting this value, you got 89 million flops in the past convolution layer only. Then in the second convolutional layer, our input feature map now 224 cross 224 cross 64, which is this output is now input to this. Here our filter size or kernel size is 3 cross 3. Then our number of filter is 64. And all this value when I put here, we got 1852 million parameters. Like this, when we putting all this value and we calculated, then finally this one, like for the dense layer, the value like n in into n out plus n out, when we put like 25008 after the flatten, This one is the input, and this is the number of neurons present in the fast dense layer. Then this is the N out, like the number of neurons present. Then the value is 102 million. So gradually, when we calculate all the dense layer and all the values, then here we can see the flop from the BGG16 is 15.48 billion. You can see all the flop value after each convolution layer. I have put it as a table here. You can see the flop value, how big it is. So why now people, you can ask me, why now people are interested to reduce those flop value or the parameter value? Because now AI is very popular everywhere. Because of the edge computing, or maybe when you have to go for some inference at the edge layer means suppose you have some real time application, and it like suppose the number plate, like when we want to see whether the car has the correct number plate or not, then the camera is running and it should check because the vehicle is moving very fast. So it is a real time one, so it can capture the image and it can, like analyze it and give you the output even if within fraction of second or 2 second max, 1 or 2 seconds, because the vehicle are moving so speed. So in that case, if the computational complexity or the time complexity will be higher, if the more, then it's very difficult to get the output within the time frame, within the certain time frame. That's why people are doing for that thing. Second thing is, when we go to deployment at the edge devices, the memory capacity or the processing unit is not that much big. So to handle those big computational parameter model is also difficult task. So how can we reduce the size of the model? So maybe with smaller computational complexity, with smaller size of the model, we put inside the edge devices. So that for that two issues, generally people are currently doing to reduce those parameters value, those flops value. So many researchers, actually mostly current paper I have found many, especially those researchers who work on Internet of Things or edge computing or cloud computing or federated learning concept, they are mostly have paper publication related to that. Very, very high ranking journals in IEEE elsewhere. So now after calculating those flops, if we will go for the calculation of MSE, the formula is 1 MSE is equal to 2 flops. So means we have already calculated this many million or billion flops. When we calculate these flops, it gives us 7738 MSE. Now when we go for calculation of the inference time, the formula is a small s divided by capital S. And let's say we have a GPU, whose CPU capacity is 1 gigaflops. Then if we divided this value, then we got 15.476 second. So you see 15 second or around 16 second is very, very high. So this is like how generally those number of parameter and flops and those are calculated. Here I just give you an example, but if any students will interested to continue the work on these areas, then we have many good publications and also some research issues we can discuss and also we can do. Okay, so this is the part actually today I will discuss this one. The previous part is just like if someone asked me, I prepared some PPT to explain that part. How generally number of parameter flops in each model we are generally calculating and how large the value is. So now let's discuss about our class or data imbalance problem. It is a global problem actually. Uh, Anybody who is working on the application of artificial intelligence, whether it is a medical or non-medical like data, definitely they face this situation. So it is, we can say, a global crisis. So what is exactly the data and class imbalance problem is nothing but you have an imbalance class, means you have one majority class or one is the minority class. Minority class means, for example, here you have like you want to classify some persons. Here you can see like with hat, without hat. Suppose you want to classify. Here you can see maybe you have less image related to wearing hat and very like big image, like very large number of images related to the people who are not wearing the hat. So there is a class imbalance, we can say, minority and majority class. Also in some cases, for example, suppose you want to know whether how many persons have the normal gene, if there is a gene effect, or they don't have the cancerous gene, or doesn't, or have the cancerous gene. Maybe here we can see the oncogene, or maybe the cancerous gene only 10%, where most of the, like, we are like the normal people, we are like the normal gene. So here the normal gene is like majority class, but the oncogene, or the gene which have some like already some mutation there, so modification there, so already they have some cancerous part is there, maybe that population is not very large, so there is a imbalance of the class, or imbalance of the data, we generally say. So what if we will give the like the imbalance data to the model? The first thing is, of course, we will not get the good accuracy, because the majority class always bias the effect of the minority class. Because we have already discussed many times how a model will learn from the picture extraction. So if one class is very high, the number of images, let's say cat and dog, and cat, like here I have given example like cat, dog, parrot, I have give one images of rabbit, and all are very high. So the model will learn about cat, will learn about dog, will learn about the parrot, but it has just one or two images related to rabbit. Then the model couldn't guess what exactly it is. Then it might tell, because maybe the rabbit color is little bit lighter, which is might be similar with the cat, or the eye, or the ear. So it will check if this image, which one is the nearest, like which one is suitable, the pictures which I have learned, so which one is the more suitable to that. Let's say it is predicted as a cat, so it is a wrong prediction. So always the majority class, we can say, dominate the effect of the minority class, so we generally get very wrong prediction. So this is the problems due to the class imbalance problem. Then how to handle those imbalanced data? The first thing is, of course, that one we always prefer, especially in the medical field, to collect more data related to the minority class. Because when we have a data imbalance, let's say we have more normal patient and we have less stroke patient, or we have more non-cancerous patient in comparison to cancer patient, we always ask to the doctor, can we get more data from the minority category? Because that one is more effective when we get the real data. So we always ask, how can we increase the size of the minority class? But the this is the advantages, but the disadvantages is, some cases, maybe for the medical images, it's very difficult to get the real image, the real data from the of the minority class. For example, we are working on the like a liver cancer, that is cholangiocarcinoma. Here the population size is actually very less. I don't know about other country, but in Taiwan actually the size is if we comparison with the hepatocellular carcinoma, SCC is highest in Taiwan, but cholangiocarcinoma is not very high. So when we want to classify between SCC and who person has the CC, like cholangiocarcinoma, actually we didn't get good accuracy, because most of patients they misclassified as most of the CC patient misclassified as SCC. It's because of the data imbalance. So we asked doctor, can we get more patients, more subjects related to the CC? Then as there is no data, the doctor can't help us even if. So that's the thing. From some medical images data, generally collect more data for related to the minority class is a very is a very big problem. So for some other images is fine, but this solution may be not suitable to the medical data. Then the second thing is the oversampling or off-sampling of the data. What is the oversampling of the data? Increase the instances of the minority class. Let's say this is your original data set. This is your majority class, the blue color. The orange color is the minority class. According to the oversampling rules, why not keep the copies the multiple minority class? Here, let's say here we have 80. Here we have 20. To map with the 80, why not copies the 20, 20, 20, 20, 20, 20 here? Okay, now what's the problem? Your solution is like you got the like the solution now, both of the data are balanced. This is 80, this is the 80. But disadvantages is overfitting. What is overfitting? Overfitting means here your model only, although it can see 80 images, but it is not just a copy of the 20 images. So your model can actually know the features from the 20 images, not from the 80 images. So model, when you give another little variation of the model, variation of the image, maybe suppose you are here the cat from the front view you are giving. Maybe a cat is playing inside a home. When you give this image, the model cannot predict because model can only know the features from these 20 images. So your training accuracy may be very high, like around 100% or 95%. But when you give the testing of images, model will fail. So that one we call the overfitting problem that we have already discussed. So, but some cases also people are following the oversampling. So, what are the method to handle those to do the oversampling? The first thing is the random replacement. Random replacement means why just only this 20, 20, 20, 20 will give. Suppose we have something like from this minority class, we randomly take some images and do the duplication. Not like suppose we have 80% of this, suppose we have this cat images and one dog images. So like not one dog images, maybe 10 to 20 dog images. Not all 10 or 20 you are going to like oversampling. Maybe we will take maybe image number 3, image number 7, image number 9 and make the copy. So this one is kind of like a random replacement. You are not exactly copy all those 10 or 15. You will consider some random images from those pool from the minority class and make them copy. So this one is like oversampling by random replacement or oversampling with shrinkage. Shrinkage means you will add some you will go for some kind of a, well, you will add some kind of a small noise or small variation to the image. Not really you will go for the data augmentation. Suppose in this case, you have many cat images, but you have just only one dog images, let's say. So you will just do little modification. Maybe you will add some little noise to that, or maybe little small effects to this image to create a variety of cat images. So it said, instead of overfitting, now you can reduce somehow the overfitting problem because you are not giving the exact image of the dog. Now in somehow you are giving little variation of the dog images. So it's also kind of an oversampling technique. Then another one we have already discussed, oversampling with the data augmentation. Like you can do some kind of external modification to the image. This one actually the internal modification means you are changing the pixels, but here you are changing the external. External means you will go for some kind of rotation, you will go for some kind of rescaling, you will go for some kind of flipping. So you are changing the external parameter, sorry, the external appearance of the image. So this is the data augmentation. In this also, in this way also you are increasing, you can increase the data size. This part we have already discussed, like like how to do like different data augmentation method, rotation, shearing, rescaling. So we have already discussed this part many times about the data augmentation. Then this one is the oversampling. That is one way to increase the size of the minority class. Then we come the undersampling or downsampling. What it is that some researchers said, why will increase the size of the minority class? Why not decrease the size of the majority class? So it's just like this. If this one is your minority class, this one is your majority class, why not decrease the size of the majority class, which is equal to the minority class? The advantages is, of course, your runtime can be improved. Now your data size small. So less is the data size, your computational complexity will be low, and also your time complexity will be low, and solves the memory problems, of course. But the disadvantages is like a big problem. Here you can see the loss of useful information. Because when you are decreasing the data size, it might like that, it might happen. Let's say there are 80 images or 100 images, and that 100 images contains a variety of features, but the model can learn to predict it is a dog or predict it is a cat. But you are already reducing the number of images. it might happen that some of the important feature, because each image will tell you a story. So while you are reducing the number of images, maybe some important parameters or important features which has, helpful for the classification or the detection task is already gone. So that also a big problem. Maybe some useful influential feature already missed. And of course, the risk of developing an overfit model. In how way? Maybe when you are reducing those images, maybe the number of the images which you have already discarded, or like there are some variety, so that variety gone. Maybe the 20 images you are keep here, these are kind of like similar images. So model ultimately is going to train with similar images, so it's somehow will go for the model overfitting. So, but people are some are doing also like the undersampling. So to handle those issues, like the random undersampling. Random undersampling means, let's say we have majority class maybe 100. We will we will not go for any kind of when we're going for the reduction of the majority class, we'll select randomly maybe image 2, image 5, image 15, image 20, image 35, and we will only replace those images. So it's kind of like a random replacement. That method also people are doing. Yeah, this part also a very one, merging a near identical classes. Okay, 2 minutes break. It's too cold, so my nose got stuck. Okay, so next we'll go for the merging of near identical classes. Actually, this technique we have used currently also in our experiment. Here you can see, suppose you have like one class turtle, then you have some kind of angelfish, then you have some goldfish, then you have some clownfish. Suppose you want to classify among these 4 classes, but here you can see the number of data present in the turtle or all those fish classes are very imbalanced. If we'll go for a classification problem, then we'll not get good accuracy. So what generally we do, if we'll find the similar classes, because these all are the fish class, maybe they are angelfish, goldfish, clownfish, X-fish, Y-fish, but they all are belong to fish. So why not merge the classes and give them another name? So like this, all these pieces, what's the common properties? They all are the aquarium fish. We can put these pieces in our home, in our aquarium. So let's they merge these 3 classes and make another new class and give them aquarium fish. So now your classification between turtle and the aquarium fish, you see now you can get some kind of balanced data. Instead of this 4 class, now you have 2 class with the balanced data. Actually, these things happened. The example I have given you, the cholangiocarcinoma and hepatocellular carcinoma, when we have less data and we are not able to get more data, so we think both are like high risk. Cholangiocarcinoma also high risk, hepatocellular carcinoma also high risk. So instead of classifying them, we make a new class, high risk cancer group. So in that one, SCC also there, CC also there. So in like this, in our real experiment also, we have done this one. But here you need to see the class you are merging, that very important. There should be a common factor between them. It's not like you will mix fish with the frog. There should be fish, and the fish is not like these are the aquarium fish. If there is a shark, of course you cannot mix the shark with them, because shark properties is very different. You need to find some common properties. If you want to merge shark with the goldfish, then you should find what could be a common properties, because that you should mention, yeah, what is the common properties between a goldfish and a shark. So always we are merging the nearby classes which have some common properties. But this is one way of handling also the data imbalance. Then the third one is the removal of the redundant information, or which doesn't have like the duplication, which or which doesn't have any, they don't have any helpfulness towards your classification or any kind of your computer vision task. They don't have any contribution towards it. For example, this is a whole slide image. So when we go for generally whole slide image experiment, here you can see actually the size is around 5 GB. And when we open in our PC or something, here we can see actually this part is the tissue part, which contains the tumor, which is already taken from the patient. But the tiling part, here you can see the background, the surrounding part is there like some empty tiles. These are actually the redundant information. Why we will keep those information? So generally with this part, we always remove from the image. We generally call that is the tile curation. Now you can see instead of this whole image, we got this image. So this part may be very high, majority. This part may be very low, minority. Now some part we have already removed. So somehow we have a balanced class. So this is also one method to handle the class imbalance problem. Then another thing we come, another after from the oversampling and undersampling on this one is the class weight adjustment. This one I used in my ischemic stroke analysis, data analysis. It's just like we will give some weight because let's say we have a class stroke and non-stroke. And here in the stroke image and non-stroke image, yesterday we have already discussed within 12 hours, it looks very similar. So the model cannot know, okay, which one is the stroke, which one is the non-stroke one, which class. Like yesterday also, I remember one student asked me, if two food images are very much similar, how you handle this problem? Actually, that also we go for the class weight. Class weight means especially for our stroke, non-stroke one, what could be the important one? The important one is always the stroke one because always our intention is to find out which patient is having stroke. Means the stroke patient should give higher importance in comparison to the non-stroke patient. So I will give you another example. Let's in a class there are some average student and there are some good student. So generally teachers give more attention towards the average student so that they can do good in their final examination. Because who are the bright student, ultimately they will get the good result. So always always the teachers give importance to the below average or the average students. It's just like that. Why not? To get the good accuracy, we will give some weight to certain classes. So for that, what's that one in the scikit-learn? Actually, there is a function utils library. Generally, by default, when we go for we'll take any model, any CNN model, this class weight is actually none, like the default one. Like every class is the similar weight. Like in a class, all students are the same. There is no average or there is no bright student. But if we'll mention the class weight is equal to balanced, that word balanced. If none means no weight, but if we'll give a balance, or we can give some manual weight. If we'll give the balance, this keyword, then the model automatically gives some weight based on the data you are giving, based on the features it is learning. Or you can also manually give the weight to your classes. Then why it is required? Here I'm going to explain you mathematically how exactly that weight has some importance. When we put the class weight is equal to balanced, how model is giving to the weight to the classes. So the balance weight of any class, the model is calculated, let's say WC, total number of samples divided by number of class into number of samples in class C. Let's say we have two classes, non-stroke classes, which is class 0 or the normal patient. Let's say we have 42617 patient data. But for the stroke class, let's say we have 783 minority class. Now, when we calculate the weight, how machine will give the weight to those classes? The total number of samples we have will include majority class plus minority class. We have 43400. Now, balance weight for class 0, the non-stroke one, is equal to total number of samples is 43400. Number of classes, how many number of classes? We have two classes, class 0, class 1, into number of samples. So, total number of sample is 42617. So, here the class weight is 0.509. But when we come to the minority class or the stroke class, here we can see 43400 is the total number of samples. Number of classes is equal to 2. And the total number of samples for minority class is 783. So it's 783. So here the class weight value is 27.713. So now you see, now the weight of the stroke class is higher. So that's even if it is minority class, now the weight is higher, means when the model will go for the feature extraction or go for some kind of prediction, now it will give more weight or more attention towards the stroke class in comparison to the non-stroke. So in that way, the non-stroke class or the normal class now no way overshadow the impact of the stroke class. So that imbalance problem is somehow handled. But here I have also put the image net. Let's say we have 10 classes and the total number of images here we can see is a very imbalanced from, you can see. And when I import the classes, we give the balance data. Here we can see the class weight. We're giving different weights. For each class, the model will calculate. Here you can see which one is the having the lower number of parameters. Like class 9, here we can see only 152 instances, and it consider 15 the weight one. So now you can see the less is the number of instances in a class, the higher is the weight. So this one, I hope you understand what's the use of the class weight, somehow handling the majority and minority of the data. Now we'll go for another thing. We'll go for the modification of the loss function. Yesterday I have shown you that bounding box detection actually is very much important in that one. For the detection problem, generally we go for the focal loss. And it was personally I used this one and I saw my accuracy actually really improved. So what happened when we go for we just generally use the SST or FRCNN on those models. So when we go for the detection, let's say in this image, we want to detect the person and the horse, the dog, like the animal and the person who are available, who are present in this image. But here we have a problem of the foreground and background imbalance. What is the foreground and background? Here you can see this one. Let's say our foreground, the image which we are going to detect, and these are the background, like the grasses, the sky, the pond. These are like the background. So here we can see the background part is much higher or the dominance over the foreground part. So it's some kind of like, here we can see imbalance, data imbalance, or we can see here like many negatives and few positives. So in this case, how the focal loss is going to help us. Here I put you an example for this for the explanation. The example is for any particular class X, generally by default, what we are using, most of the person like us also we are using cross entropy function because this one is very much popular. Let's say we are only use the cross entropy loss function, will not use the focal loss. What's the problem? Generally, for the mathematical formula, how to calculate the cross entropy is minus log px, where x is the class and px is the probability of the class prediction. Let us consider we have two classes, non-stroke, we have like majority classes, and this is with the prediction probability because the loss function we have calculated, I have already shown you. I have already told you also how the loss, because if we want to achieve 100% accuracy and we achieve 0.99, that means our loss is 1%. So let's say with these classes, for this class, we got the prediction probability 0.99. And for the stroke class, let's say we have only 10 and we got the probability 0.01 only. So the cross entropy loss considering all samples for class 0 when we put, so this minus log px value when we put, here we can see the value is 4364. But when we go for the class 1, for the minority class, when we predict, it is only 20 when we put this value. So now the loss contribution for the non-stroke is how much? So total we have how much value? 4364 plus 20 is the total loss of the model. And out of this total loss, you can see non-stroke is 4364. When we have divided into, we have 99.54%. However, for the stroke class, only 45%. So non-stroke class, which is the majority class, has more contribution towards the loss than the stroke. So more contribution towards loss means model will say, okay, if it has more loss means I need to update my parameter to minimize this big loss, not the small loss. So then anyway, you somehow your loss function is biased towards the majority class in comparison to the minority class. If we use the cross entropy one, but if we'll go for the, let's say, the focal loss one, then the formula is, they have one come up with the formula FLPT is the minus alpha t by 1 minus pt by sigma by log pt. So what is that one? They are actually introducing some scaling value, which is range up to 5. The default is 2. And this one is the class probability. And this alpha t is nothing but a prefixed value between 0 and 1. The default value is 0.25, but you can hypertune this value based on your application. Let's see when I put this value, what we will get. We'll consider the same application, the non-stroke classes, and also the stroke classes, majority and minority. And with for the non-stroke class, let's the prediction is very, probability is 0.99, where the stroke classes, thus the prediction is 0.01. And the alpha t value I consider 0.25 for class 0 and 0.75 for class 1. And the sigma value, this value I have considered 2. When I for class 0, for the non-stroke class, when I put, now the loss value is 0.32. But for the stroke class, for the minority class, when I put this value is 4.901. Now when we go for the loss contribution for the individual classes, now you can see for class 0, this one is 6.26%. Sorry, this one is 1. Now, for the class 0, here we can see when we put these values in this formula, we get 6.26%. But for the minority class, which is class 1, now the loss contribution is 93.74. You see, from the previous one, the majority class is the higher loss contribution, where the minority class is less. But here now, after using the focal loss, the majority class loss reduction is reduced, loss contribution is reduced in comparison to the minority class. Now model will more focus towards the minority class, not the majority class. So this one like one example, how focal loss is helpful or somehow internally to contribute that majority and minority part. Then we go for another mechanism. That one is the level smoothing. What is the level smoothing and how why it comes to the picture? Actually, level smoothing is mostly we use when we find there is a problem in the label itself. Because when, especially in the medical images, some of the lesion or some of the ROI, even if doctor confused, they make it, maybe it's the SCC, they make it CC, or maybe it is a benign tumor. Sometimes they think it is a cancerous tumor. So there is some mislabeling. Yeah, right. That's why I give you an example. Let's say these are the dog, these are the cat. Maybe somehow this cat is mislabeled as dog. So there is a model confusion arises. The model will see, okay, these are the dog, fine, because the model will learn from the label. These are the cat, fine, but this one looks like this category, but labeled from this category. So some kind of majority and minority, again the class imbalance arises based upon this wrong labeling, because the model will say this type of image is available here, but the label is not there. This label is available in this class, but no image is like this. So some kind of imbalance. So for that class, we are using the label smoothing concept. But what's that label smoothing concept? To relax the confidence on the labels. Okay, sometimes, for instance, we can slightly lower the loss target value, because always when we go for a classification, suppose we want to test an image, it is a cancer image. So ultimately we want to get for the cancer image 100% accuracy, and for the non-cancerers at that time 0%. If we go for a binary one, the outcome always should be like 1 and the other class should be 0. That always we want to achieve. So here how we can use, instead of giving 1 and 0, let's say we're giving the label example cat is equal to 1 and dog is equal to 0, because model will learn 1 and 0 in such a that instead of just giving 100% accuracy we want to achieve for 1, and 0% accuracy for another class, why not we use a regularizer, not give 100% confidence to one class? How about that confidence we will reduce a little? I'll give you another example. It may happen that some students are very overconfident generally in a class. So what generally they think they read 10 problems and they said whatever we have learned, it's like definitely like we are so much confident and we can solve any problem. However, we will reduce that confidence a little. Instead of that giving them that 10-1, we'll regularize their confidence. We'll give them a difficult question and we can say, can you solve this? Then definitely they cannot, because they have all like already learned everything from that 10 questions only. So some kind of model, like to reduce that overconfidence problem in the prediction, we'll use this regularizer. So here 1 hot levels, generally machine will learn 0 and 1. The formula is 1 minus label smoothing plus label smoothing. So here 1 hot labels like 0 and 1, let's say cat and dog, then 1 minus 0.2, the label smoothing or regularizer value is 0.2 plus 0.2 by 2. So here instead of, when we give an image of the cat, and instead of giving it is 1 or 0 directly 100%, and for the dog 0%, now it is giving us 0.9 and 0.1, means there is still a chances of improvement. So when it is getting 0.9, the model definitely will check, oh, it is 0.9, might be a chance the model might, the image might be dog, because that is also for dog, the accuracy is 0.1. The model again go for back propagation. So instead of at one time give one result like finally, no, it is a cat image, I am 100% accurate. Why not? It will say it is a cat image, but I have 90% confident. I have still 10% up and down. So that 10% will helpful for our model improvement. So if any images is like it is a cat image but mislabeled with dog, and for this image it might tell us it is cat 100%, but there is a chance also it might be a dog image. So there is also model will go for another round of evaluation. So that one actually used for the case, this is actually the case of level smoothing. We'll use actually like a regularizer parameter to minimize the confidence level of the model for any outcome. Then, but the level smoothing, the disadvantages is it not perform good when the loss is lowered for the wrong classification. Sometimes actually the model really predict wrong classification, and we thought maybe this wrong classification is because of overconfidence net, but no, the model is actually predicting is the wrong. And if you have less number of classes, then let's say for 1, 2 classes or 3 classes, then level smoothing is not advisable. When you have many number of classes and there is a high chance of level mismatch, then in that case it's better to use the level smoothing. Then the final one, that if anything will not work, then if we need to increase the size of the minority class, then currently the synthetic data generation, the generative adversarial neural network is very popular. So what's the synthetic data we can generate? The first thing is it reduce cost and higher accuracy, because for the, when we go for some kind of, again the data, if will ask for more data, then we need to give more cost, expensive. So that cost part is reduced because now we can generate our own data. Then model scalability is increased, because with synthetic data, we can create a vast amount of data, a variety of data. And of course, the create data sample for edge cases. For example, if some images, we have very less number in the real world, but with this data augmentation, we can create more number of images. Then what generally currently people are using, generative adversarial neural network. You people have already maybe heard about that. So I'm just going to give, because this one is very popular. So GAN I'm going to use, maybe actually this GAN part we might need in our medical image data. So here actually in the GAN, there is two part. One is the generator network and one is discriminator network. Both are actually the CNN, but there is two network. Instead of a one network, we have a generator, one is our discriminator. The generator network job is to generate fake data. Means it will generate the data actually. What is the role of the discriminator? Every time the data is generated, the discriminator will check it is a real data or the fake data until you get the real data. Means until you fool the discriminator. So because your ultimate aim is to generate the synthetic data which looks like the real data. So when the generator will generate the data, someone or some network will there which can evaluate the generated data is the real or the fake. Until the data will say it's fake, means generator is not good. Generators should generate in the data in such way that the discriminator will get full and it will say it is a real image, but actually it is a fake image. Here I give you an example. Suppose we have like a thief and he's generating like some black money. So like or some what we can say duplicate currency. So it will generate and the police will say it's a fake money, which has real knowledge about the money. Then it will again say, oh, it's a fake image. Then it said, I need to update myself and fake and make more realistic money. Then it will again generate the money. It will have it has already have the knowledge. It will say it looks like the real money, but still need to go through the details. Then it will say, no, it's a fake money. Then it will say, okay, I need to update again myself. Then it will generate the money. So in this way, there is will be like a competition between this police officer and the counterfeiter. Now, one time will come, the fake money, the discriminator cannot guess it and it will say, oh, it's a real money. Then our synthetic data generation is completed. Now we generate the fake data, but it is actually the real data. So now our generator is the winner and discriminator is the fool. So now you can say I can print fake, I can like print fake money. So it kind of like a data augmentation now we can do. So in that way, actually we are generating the synthetic data. So it's just like how the CNN and GNN there. CNN, we have only one network. In the GNN, we have a generator network, will generate the image. And this is the discriminator network, which will tell it is a real or the fake one. So how the structure of the GNN actually? We have the generator, the input. Here we are giving like a random samples. From that it will generate an image. Then how the discriminator will check the image is generated is real or fake. We also give discriminate the real image, how the real image looks like, so that it can have a comparison based on this real and generated image. Then it will tell us this image is the real or a fake. So first it will go for the how the input is generated. We will go for some kind of latent samples or the random noise. For that we are generally using the uniform distribution or normal distribution. It will give us some pixel value, and this value may be some kind of age, color, sharpness, intensity, and of dimension, like we'll store them like in a latent space. Then when we give this value to the generator network, the generator network will generate this value, this fake image. Now the discriminator will check, because the discriminator are already trained with the real image. Now it will check your generated image, whether it is a real or the fake. Until it get full, it will get full and tell it is a real image. So the discriminator network always intention is to tell it is fake, until it has like it cannot know, okay, this is a fake image because it looks like a real image. So that's why there is always a competition between the generator and a discriminator. The generator always try to generate the image in such a way that it looks like real. The discriminator will always try to the generated image always try to tell it is fake. So this task always make it real, this task always tell it fake. So there is a competition between them. So here the generator aim is to fool the discriminator, and the discriminator job is not to be fooled by the generator or catch lies to the generator. So there is always a win-win situation. The generator always said, I want to win. The discriminator says, no, I want to win. So here the generator always try to minimize the loss function. This one is also discriminator always try, no, I will minimize my loss function. So it will say minimize the value function. Here it will maximize the value function. So there is always a min-max game between the discriminator as well as the generator when the model is training. So generally they have the confusion matrix. Like through this confusion matrix, how you know? Because there is two network. One is generator network, one is discriminator network. So how you know the generator network needs updation or the discriminator network need updation? Through this confusion matrix. So this confusion matrix means let's your image is fake and your discriminator will say it is fake. Means who needs to update it? The generator needs to update it, means the generator is generating a fake image and the discriminator also say it's a fake, means the generator should update itself in such a way that it will generate a real image that the discriminator cannot get it. So in such scenario, the past scenario, when it is fake and the discriminator say fake, means true positive, the generator needs to update it. Then the second scenario, when it is a fake image, but the discriminator say, no, it's a real image. Means who needs to be updated? The discriminator needs to be updated because it is a fake, but it say it is a real. So means there is a problem in the discriminator. You will update your discriminator network. Then the third part, when it is a real image and the discriminator will say it is a fake image, means at that time you are already generating a real image, means the generator already reeling kind of a real image, but every time your generator say it is a fake, means the discriminator actually is do good because it is a fake image, but the according to generator it is a real image. So in this case the generator has really done very good job correctly, but the discriminator can do better. So in this case, the discriminator needs to be work once you need to modification of the discriminator. Then the true negative. Neither the discriminator is good nor the like the generator is good. Now the discriminator cannot is not generating a real image. Sorry, the discriminator is generating a real image and it is saying a real image. So it's a kind of like everybody, no need any updation. So it is kind of like a confusion matrix scenario. Here we can see generator need updation or discriminator need updation. But up to what time, like how they are updated, like every time the generator generates something, then the discriminator will go through, then there is a back propagation. So every time there is, like we can say a model updates, but up to what point the model will update until it will reach the Nash equilibrium. What is the Nash equilibrium? Means like at each epoch, this is the generator, this is the discriminator, they will update itself. So at one time come, the generator will generate an image and the discriminator cannot like tell it is a fake image, it is a real image. We generally reach a equilibrium point. Or the generator every time generate any image, the discriminator will say a fake image. So now your generator network cannot generate any image which looks like real. So two cases, either one generator like stops of generating real images because every time is generating the fake images, the discriminator can catch it, or generator will generate such a real image, the discriminator cannot catch it. So in that both of the case, we'll say the equilibrium point we have already reached. So this one we generally call the Nash equilibrium point. Actually, many maths behind this. So these are some steps. How can you train your GN? But I think these points are not important for you now. If anybody will go for synthetic data generation, we'll go for that. Then currently some application, people are using some kind of like dynamic character generation or pose guided image generation or some kind of, like in the fashion industry, actually this GI synthetic data is very popular now. If you want to like some kind of resolution, if you want to increase, or now this part also in Facebook is very popular, when you have some other kind of like destination and some other destination now merging of two picture, we call it the image registration. So in such cases also GN is very popular. Or text to image generation, some application like DiscoGN, maybe you have one input and you want to see this color in another output. Suppose you buy this bag and you want to see what kind of swoosh I need to like take in. So some kind of through GN, you can also choose your swoosh color. and some kind of now face aging also very popular. Actually, they have using generative adversarial neural network. Like now, suppose this is your age when you are going to be 60, how you looks like. Suppose, and also like your face now looks like which kind of celebrity. So in Facebook is now very popular on those. Actually, they are using in background generative adversarial neural network. Some application, this is one paper like I have put. Their task is to find out actually these are the eye, the retina image. Actually they want to find out is there any problem in the retina image, whether there is any obstruction, or there is some narrowness, or there is some blood clot inside that one. But they don't have this much images related to that. So for that one they have also used the generator and discriminator network to generate the synthetic data in this paper. And here they actually find out the tumor of this one IEEE transaction this paper has published. And they have also used some kind of this synthetic image generation to generate the MRI image. Their alternate aim is to find out the tumor. And this paper actually published by Dr. Gupta, and the last time in the brain, in the liver tumor, actually she used DCGA and actually the synthetic image generation. And here you can see this is like the without generation, the input, like when these go for the, she used DCGA method. This is an input model, input images for the to the synthetic this model DCGA, and these are the output. Here you can see just looks like the real image. So use actually this because we couldn't get much liver data from the doctor. So then we have to apply this DCG and synthetic data. And with synthetic data also, she got very good accuracy. So her paper is already published. So these are like different methods. GN method also there. You can apply those things based on your application. But there are also some problems. The first one is the problems in the counting. Suppose we found also some problem like this. When you want to generate some kind of images, let's say some kind of animal images or some kind of tumor images, and if that person is having 2 3 tumor, when there is a counter one, this type of images we are getting, maybe in the synthetic image there are already 15 to 20 tumors, or maybe 2 tumors already gone. So that part also the synthetic image we say doesn't work really well. And problems with perspectives. Let's say you have some images where the dog is sleeping, or the dog is roaming, or the cat is inside a bed. So in that cases, when there is a 3D view comes to the picture, the synthetic data like the GN is really not working well. And the global structure, like when you are presenting a global structure, suppose 2 dogs are there, or the dog is sleeping but putting the head inside the body, so in or some snake is crawling. So when it is taking a global context of the image, also it fails. And the sensitivity is like something like if either the discriminator generator gets better than other too quickly, so nobody can catch. So if generator is like update itself too quickly, then discriminator cannot catch, or discriminator can update too quickly, then generator cannot catch. So this is like one is always better than the other, but like every time. So once the generator will get better, the discriminator cannot get it. The next epoch discriminator is better, the generator is not. So in every epoch, so there should be a pattern, either generator is good, or discriminator is good. But at one time, in one epoch discriminator result is high, at one time generator result is high. So at that time actually there is a sensitivity issue. Or the oscillation means nobody can reach to the equilibrium point. So there is already oscillation between the discriminator and the generator. For that oscillation, actually, we are using the solution is the extensive hyperparameter search or the vanishing gradient problem. When generator gets like too good, too fast, generator or can learn to pull the discriminator consistently, will stop learn anything. Means in this case, your generator is too good, like within 2 3 epoch, it will generate such real images. Means the discriminator cannot learn anything, but cannot catch those images. So we generally call this kind of a vanishing gradient problem. Then we have big samples. Big sample means if your sample large size, like around 1000 cross 1000, if your image size is too large and you want to generate a synthetic image of a big large size, then it is a problem actually. Like for synthetic image, large size of image, it is really not giving good result that we have seen. So what will give the solution? Maybe the big images, either you can resize it or make it small, small tiling, then you can do it. Because this situation happened, I found in the Dr. Gupta's case also. When you give the entire image with the liver tumor, we are not getting good accuracy. But when we are cropping only the tumor part, when you are giving the GAN model, it gives us better image. So the big sample actually is a real problem. Then of course the model collapse. Like either the generator will like always generate a, like the real image, but the same real image. So the discriminator will say, no, it's a real image, it's a real image, it's a real image, but there is no variety from the generator. So maybe you will generate the synthetic image, 500 synthetic images, but that 500 images all similar. All, so there is no variation. In that case, we said the model collapsed. The generator already collapsed. It cannot generate a variety of images. So these are some challenges related to the GAN. So we have discussed many applications like where we can apply the majority, and some methods where we can apply the some methods to minimize the data class imbalance problem, or to get a balanced data on how the synthetic data can be applied. So okay, any doubt?
Yes, it's open
Good
for
morning,
all.
ma'am.
Yes.
Yeah.
Ma'am, this is a little bit off topic, but when you are in first 10 to 15 minutes, you have explained to choosing the GPU thing.
Oh yeah.
Ma'am, like in I have done a like workshop on the chip designing and semiconductor, but there they
Oh yeah.
say like the middle part of the wafer is always the best for making any GPU or anything, and the side
Okay.
parts are little bit off and give errors. So, like
Okay.
in that CNN, we are using the GPU. So, will it create data error or it will not affect the data?
Honestly saying, that the GPU, that the chip part, I really don't have much knowledge towards the hardware. Like mm, the one you were asking, if it is like the hardware related part, then I cannot say you now. Maybe I'll need to go through that because the
No,
chip
ma'am. I was
designing part,
asking like the
Mhm.
GPU, their GPU, like they have some error in the GPU designing. So that
Mhm.
error might create error in CNN, like image
Oh
production
yeah,
or
yeah, yeah,
image.
yeah. Actually, that happened. I
Yes, ma'am.
remember
I
in
was
our
asking that.
in our PhD. We bought one GPU. That one is really working well. I forgot the name. I think it's 1070 Ti. The next one I
Mhm.
were bidding, we bought is 1080 Ti. So 1080 Ti should work better than 1070 Ti because it's the advanced one.
Yes,
But
ma'am.
we saw the classification accuracy, it is not giving good, taking too much time. And we found also some kind of, the bias issue means the part like when we are giving, because in one epoch it is giving us very good. One time I learned the train the data, it is giving good result. The same data I trained another time, it give me some very strange result. So when we check, there is some usage inside that data bitting error. They said when, because the model can check because this is a computer, it can only know the binary value 0 and 1. So in that GPU, actually the problem is some kind of bitting error they said inside their, I forgot the name, what's the component name they said. So that part is actually the error was there. Then it's go for some kind of, maintenance. Then now the issue has been solved. This is, I
Yes,
forgot the name actually. What's that one? They said that when that converted into bit byte error, so that problem is happened. So when we are giving the image, for us it is a pixel value, but when we're giving the label like 0 and 1, so because of that error, we are getting that like output, the wrong output.
yes,
Yeah, it
ma'am.
has some GPU. Yeah.
My mentor on that workshop said that the middle wafer part is sold for like special edition, and the most outer part which is given as normal. So that contain errors.
Maybe actually, I don't know, but practically we face this situation because of some of GPU internal part from the chip design. I don't know what's that part. We got actually the CNN has gave us very bad accuracy.
Mm. Thank you, ma'am.
Yeah.
Any other questions? Pushpa ma'am is also here, huh? So you can ask question to both. No problem. You can share also video.
If no more questions related to
Yeah, sir,
Ma'am, I
there
have
is
a
some
question.
question.
yeah, please.
Actually, I was thinking that uh, is the flops and these max metrics, are these device dependent, as in, is it model dependent or device dependent? I got confused along the way, actually.
Okay. If it is capital S, then it is device embedded. But if it is small s, it is model dependent.
Okay, I think I get it. Okay.
Yeah, because the props we can let's go to here. We have the formula for each layer. We are calculate the props.
So the
But
less
Mhm.
flops, there is the more lightweight it is, right? So it's more
Yes,
efficient for like
yeah,
if I want to run natively on my phone or something.
exactly. You took the right point. The right word is the lightweight. Yes.
Okay, okay. Thank you.
So now many apps are there. You will just capture the image and the machine learning or deep learning is learning, so it's running somewhere, and it will give at any instant it give you just like the result. So for that, especially for the mobile age or the edge computing, generally this lightweight model are very popular. Okay, please ask.
Yes, ma'am. I have a query.
Yes.
Actually, it's not related to this presentation.
Uh-huh.
So, a few days earlier, I was
Yeah.
searching something in this chat GPT, and
Mm-hmm.
a few days earlier, I was searching something in the chat GPT, and chat
Yeah.
GPT pointed a thing that when we
Mm-hmm.
apply this synthetic data
Mm-hmm.
before train test splitting, so there is a
Mm-hmm.
issue of data leakage in the
Oh
test
yeah.
sample. Uh,
Yeah.
so the ultimately the training accuracy and testing
Mm-hmm.
accuracy both increases, but which is
Mm-hmm.
mainly due to the data leakage. So I just
Yeah.
want to verify that point actually.
Yes. What is data leakage? Data leakage means some of your training data is present in your testing data. So
Yes.
that means already the model which have trained those images, maybe some part of the images are already present in the test data. What means you are always getting the test accuracy also very good. Because
Yes.
that part model already known those images, already trained with those images, and when that similar images are present in your test data, means your testing accuracy is already higher because model already trained with those data. The same data is present in the test data, so we call this the data leakage. Means some data from the trained images is already leaked to your test data. So that one is like one kind of problem. So when reviewer we got, so even if with the test data we already saw, even with the external testing we are getting very good accuracy around 90%. The reviewer always asks us, is there any data leakage? We say no. When we are partitioning the data, we are doing perfectly cross validation so that there is no data leakage. Then another question comes, like when there is a synthetic data, the chat GPT said there is a chance of data leakage because when you go for the synthetic data, when we are generating some kind of rotation or some kind of flipping, it might chance that when we go for the synthetic of the all the data, and when we are after synthesis, when we go after the data augmentation, when we go for the partition, there is a high chance that the augmented the same data is partition is present inside the test data. Means the same dog is there, maybe the horizontal flip image in the train, but the vertical flip one is the test data, but it is the same image. You got my point? So it's a
Yes.
kind of data leakage. You can say, I have already synthesized it. I have already do the flipping, and the flipping is also different. Here horizontal flipping, here vertical flipping. But no matter what may be the flipping, there is a high chance the same dog image. So the model will already learn the horizontal flipping pattern from the training. So the testing is very easy. So in that case, what we do, we always we make synthesize or we make the data augmentation only the training data. We are not touching anything in the testing data. Testing data is as it is. So always perform the data augmentation in the training data. We have always written to the reviewer, we applied the data augmentation only to the training data. Testing data, no. Testing data is just model is trained, model is freezed, we are going for the checking, we just use the test data. So in that way, we can minimize the leakage problem. Am I
Got it,
clear?
ma'am. Yes, ma'am.
Okay,
Thank you,
thank
ma'am.
you.
So Ayush and Kusagra, yes, one by one.
I just want to ask that data augmentation and GAN will be using for a small data sets, right?
Yeah.
So in that case, for let's say if we have a small data set, so how can we decide like whether to use here augmentation or GAN or use them both together?
Okay, that's a very good question also. First thing is, if the data size is small, this is not the only reason we go for the synthetic data or not. Also, even if we are higher number of data size, but there is a less variety. That one also another point. We'll go for the data augmentation or for the synthetic data generation. So the next question is whether we'll go for the data augmentation or whether we go for the synthetic data. First, we generally advise to go for the data augmentation because it's the easiest one and it is like doable fast. But sometimes it happened that even if you do some kind of data augmentation like the flipping or rotation or rescaling or the zooming, but the model always learn the same features, means that data augmentation has no impact your model on your model learning. Just like I gave you an example, this is a dog image. If you do horizontal flopping or the vertical flipping, it is the same dog image. And if your machine cannot distinguish, like it is like two different images, the machine can only learn, okay, it is a dog images. So there is no, like advantages of doing the data augmentation because machine will only learn those features. So in that case, we go for the synthetic data generation, because during the synthetic data generation, we are generating it from the noise. Because we are generating the pixel by ourselves. So there is a higher chance we will get a variety of images if comparison with the data augmentation. But first, we always advise to go for the data augmentation. If data augmentation will not work, then we go for the synthetic data generation.
Got it, ma'am. Ma'am, is there the cases that where we use the both? I mean, we did GAN and then applied data augmentation over the GAN produced images.
Actually, Dr. Gupta has done this work. She applied fast the GAN, fast the DCGAN, and I think she has applied also some data augmentation method to that.
So, ma'am, these things are basically like where we, I mean, do the experiment and check for the accuracy in that way we do, or is there any way we just find it out that first augmentation, then GAN, or do the GAN and then
No,
do
actually,
the
there is no
augmentation?
rule that you need to pass to augmentation, then GAN. Generally, when we got the data, because it's the normal one, we generally go for fast the data augmentation. Because data augmentation, I say it's easy. Fast need to do and check. If do the data augmentation accuracy is improved or not. Even if we found after applying the data augmentation, also the accuracy is not good. So at that time, but our data size also very less. Then at that time we are thinking, let's go for synthetic data generation. Then after generating synthetic data also, if we find, okay, even if because it's not like after generating the synthetic data, we like always a higher chance get the variety of images. Again, we see the accuracy is just only improving 2-3%. Then we go for how about we'll apply some data augmentation also on the synthetic data. Then with the synthetic data, we apply some data augmentation. So we can say there is some hit and trial method. The first we apply data augmentation, not succeed, then go for synthetic data, also not very good, then apply augmentation to the synthetic data, then it is improved. So it's not like a rule, like we'll apply first this one or this one. It's like we can say some steps of experiment we need to do. There is
Got
no
it, ma'am.
particular rule actually. And honestly saying, it's like kind of from your experience, you can say what kind of data set are you using. From the CT data, like Dr. Gupta's work, it works well. But for my MRI, it doesn't work well. even if I generate synthetic data, it will not increase my accuracy. So I just only use data augmentation to that. I have not used synthetic data. So that one also, how is your data? That also matter.
Basically, it's an experimental that where we are getting a good accuracy.
Actually, honestly saying, from our experience, 8 to 9 experience, I think Dr. Gupta will also agree with me. In AI, there is no standard rule. There is no standard.
Okay.
Everything we can do, we will do through experiment, hit and trial. Although people has published paper, but there is, we cannot say, okay, from the paper we can get the experience, we can get the knowledge. But as the data is different, the size is different, everything is different. At that time, what we will think, that we will do.
Thank you, ma'am.
Okay.
Yes, Kusagra. Next question.
Good afternoon, ma'am. Ma'am, I
Yeah.
have been working on some patent for a while. So my question is, if real patient data is unavailable, can we use synthetic data? Is it
Oh,
acceptable?